Welcome everyone to session 2A. Today we are going to talk about the derivative, and we're going to introduce the definition. We're going to talk about the various interpretations, and then we're going to cover when derivatives exist. So I'm going to assume that most of us have learned what average rate of change is. This is a classic middle school or maybe even elementary concept. And basically the idea is if you have a function and you have a and b, the average rate of change is just given by the rise over run, right? Rise over run. Rise is just f of b minus f of a. Run is just b minus a. We have another way of writing this, and it's just essentially writing h as the difference between b and a. And so a plus h would become b. So this is another way of writing it. Now, if I want to find the rate of change at one particular point, we call that the instantaneous rate of change. And let's say I want to find this instantaneous rate of change at x equals a. Now, graphically and intuitively, what this is just simply the slope of the line that is tangent to the graph at the point x equals a. So it is the slope of tangent at that point. And the way in which we choose to find this is that we're still going to take an average rate of change, and it's going to be on this secant that goes from a to x. So let's say we take this other point x. And what we're going to do is we're going to take the average rate of change of the secant as x approaches a. So this is exactly what this limit is doing over here. It is taking the average rate of change of the secant a to x as x approaches a. And the effect of doing this, let me illustrate here, is that its secant gets infinitely close to the tangent. And so let's say I want to take the instantaneous rate of change at x equals a. And so sort of this tangent here is the desired slope. And I have this x here at first. So this secant right over here seems to have a slope significantly greater than this slope, at least this desired slope. At least it's very much visible to us. And let's say I take this x a little bit closer right over here. Then this slope here is less than the one from before, and it seems to have gotten closer to our desired slope. So let's take another one. So here, this x, this seems to be even better. And as we keep on taking the x closer and closer, we will be approaching this tangent. And that is the ultimate idea of taking this limit. And so this is how we define the instantaneous rate of change. Now, in terms of calculus, we write this as the derivative of f at x equals a. So f prime of a denotes the derivative of f at x equals a. It's also one way you could read this. So the derivative of f at x equals a is f prime of a. And these are the ways in which we could calculate it. So sorry, I forgot to mention here, this is just the alternative way of representing this, taken straight from here. So this is the definition of the derivative. Now, to demonstrate how this works, we're going to determine the derivative of the function x squared plus 3x at x equals 2. So the way in which we're going to do this is we're going to compute this alternative limit right over here. And in fact, this is usually the easier one. Now, the AP test will not test the computation of this limit explicitly, but because what you could always do is you could convert this to finding the derivative at a point. And the method of finding a derivative of a function in general, we'll teach in our next videos, and that will make it significantly easier. So you don't have to practice this over and over, but you should know how it works. So here what we're going to do is this derivative that we want is equal to the limit as h approaches 0 of f of a plus h. So f of a a here is 2, so a is the thing that we care about, the x value that we care about. F of 2 plus h minus f of 2 over h. And this f is just x squared plus 3, right? This is the function. And we can expand this numerator right over here. So this becomes 2 plus h squared plus 3 times 2 plus h minus f of 2, that's just 10, over h. And then what we could do is we can collect like terms, and we can get h squared plus 7h plus 10 minus 10 over h. And this then we can simplify. So we are finding an equivalent fraction, right? And this is h plus 7. Now h tends to 0, and we can just substitute here. This is equal to 7. Now, this then is the derivative of the function x squared plus 3x at x equals 2. So now that we've seen how to take the derivative of a function at a particular point, we're going to generalize this to the derivative of an entire function. And the way this is going to work is that we're going to write this as f prime of x, and the f prime of a will give you the derivative at a. So it is essentially what we did there, but for x in general. And the way we're going to do this is we're just going to simply compute this, but for a general x, rather than a particular value. To illustrate this, we're just going to directly run f prime of x over this function right over here. So the derivative is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. And this is going to be equal to the limit of h to 0 of, so we're just going to directly plug this in. This is going to be and expand. This is going to be this plus h cubed plus 2x plus 2h. This is f of x plus h. And we're going to minus f of x. That's going to be this. And then we're going to take this whole thing over h. So then what we would see is that these two cancel, this also cancels, and what we're going to be left with is, I'm just going to directly simplify or write an equivalent fraction of 3x squared plus 3hx plus h squared plus 2. And as h approaches to 0, this term vanishes, this term also vanishes, and this just becomes 3x squared plus 2. So this is the derivative function of f. So this is f prime of x is just equal to this. And what is so powerful about this function is that now if I want to find the derivative of any particular point on this function, I can just directly plug this value into this f prime of x function. So this f prime represents the derivative function of f. Now, f prime of x exists if and only if this limit exists. Sometimes this limit may not exist, and if it doesn't, then it's not differentiable. If it is, then we say it is differentiable. And like in continuity, if a function is differentiable at every point, then it is a differentiable function. So now with this in mind, we're going to talk about two major interpretations of the derivative. The first one is numerical. The numerical interpretation of the derivative is just that f prime is the function that maps x to its respective instantaneous rate of change of f of x. So using the derivative, we can find that this f prime, using the same method as above, turns out to be 2x. And then with this, you can just plug in f prime of -1 equals -2. So in this numerical interpretation, f prime of x maps x, which in this instance was -1, to its respective instantaneous rate of change, which is -2. On the other hand, we have a graphical interpretation, which is that the derivative of f at a point is the slope of the line tangent to a graph of the function, which was sort of the way we defined it in the very first place and sort of what motivated us to come up with this limit. So this is the graphical interpretation. So if I were to say I want the derivative at x equals roughly -2, then it is equivalent to finding the slope of the line tangent to the graph at x equals -2. So here it would just be this. So there's the numerical instantaneous rate of change perspective and the graphical slope perspective. So besides f prime of x, if we let y be equal to f of x, these are all ways in which we can write the derivative. And if you see any of these, you know that they're all equivalent to this f prime of x. So these are just different ways to write a derivative. There's nothing really special. Feel free to take a screenshot or whatever. So now we're going to consider when a derivative does not exist. So we're going to recall that the derivative is ultimately defined by a limit. And for a limit to exist, we need the left hand and the right hand limits to exist and agree. So if we examine what the left hand limit is, this is essentially the left hand derivative at x equals a. So let's say we have x equals a. So when x approaches a from the left side, we have that h approaches 0 from the negative side, because their difference, this h, which is equal to x minus a, would be less than 0. So this x approaches from the left side, and that's why we call it the left-hand derivative. So the left limit, this is the left limit, is actually just equal to the left-hand derivative. And the right-hand derivative, it would then just be the right-hand limit. So here we have that the left and right hand limits are just the left hand and right hand derivatives. So for this limit, or for this big derivative to exist, we need to have that these two derivatives exist and agree. So now we're going to consider when derivatives do not exist. So these are the different types. So firstly, we have discontinuity. This is sort of the special case. If the function is not continuous at a point, then you literally have two places to find a derivative at, and any derivative that we get here, it really is not quite meaningful because it isn't even continuous. So if the function is not continuous, then we have, then we don't have a derivative. This makes a lot of sense. Then secondly, we have corners. So here, as noted, this is the left-hand derivative, and this is the right-hand derivative. And they represent the left and right hands of a limit. And if these two hands of a limit do not agree, then the limit, which is the derivatives, does not exist. So here, because the left and right hand derivatives do not agree, therefore the bigger derivative does not exist. So here we have one derivative on one side. This is, for example, -1, and this is 1. Then here we have disagreeing left and right hand derivatives, and therefore the derivative does not exist. Finally, we have the two cases where the left hand derivative and the right hand derivative simply do not exist. So what we have here is that for a vertical tangent, we have that both the left and right hand derivatives are positive or negative infinity. So they're either both positive or both negative. In this case here at x equals 0, for the cube root of x, we see that both the left and right hand derivatives of the function at x equals 0 is positive infinity, and therefore neither of these, really all you need is either, but neither of these derivatives exist, and so therefore the bigger derivative does not exist. So lastly, we have cusp, which is just when one side is positive infinity and the other is negative infinity. So here, for example, we have that the left-hand side gives, the left-hand derivative gives negative infinity, and the positive side gives positive infinity. So this would be a cusp, and the reason why the derivative does not exist here is because, again, the left-hand derivative and the right-hand derivative does not exist, and therefore the bigger derivative does not exist. So these are the four ways in which a derivative may not exist: cusp, vertical tangent, corners, and discontinuity. These are the four ways. But here I would like to address an edge case that we have considered for continuity but not for derivatives, and that is for endpoints. So, um, and also, sorry, for limits. We have considered this for limits. So let's say we have a function defined over AB, and then you might ask if the derivative at A and B exists. So this is derivatives at endpoints. So if you consider endpoint A, uh, the definition of its derivative is still limit h approaches 0 of f of a plus h minus f of a over h. Now notice, when h is less than 0, a plus h would be less than a. And this f a plus h would be undefined, and this whole function right over here would not be defined. So let's say you pretend this is g of h, right? So if we let this be g of h, what g of h would look like is g of h is not defined for any h's less than 0, and there would be something on its right. So for this is then we're essentially taking the limit at this endpoint, right, for g of h. So what we would be doing is that we directly take this to be its right-hand limit, right? So this is what we've established in our limits chapter. We said that if you're taking the limit of a function at an endpoint, then it's just equal to the limit of the one-handed limit of the side that exists. So here, we would just be taking the right-hand limit, a plus h minus f of a over h. And in this case, that would just be equal to the right-hand derivative. So it's just equal to the right-hand derivative if this exists, if it exists. Sometimes the right might also not exist, in which case the whole derivative would not exist. But for endpoints like a and b, there is still this way. So you still take the one-sided derivative for it to exist. And finally, we have this very small but important detail, and it is that differentiability implies continuity. The reason behind this is very simple. So if you consider, if a point is not continuous, then it is not differentiable, because this is the first type in which points are not differentiable. If you want to reason this quickly, you can just claim this is the contrapositive statement. But then more logically, you can say, or if you want to practice logical thinking skills, you can say if a point is differentiable and then if it's not continuous, then that would imply that it is differentiable as per here, and that would immediately be contradictory. So therefore, it would have to be continuous. So a differentiable point must be continuous, but then the other way around does not hold. So if you have a continuous point, that does not mean it's differentiable, as seen here in these examples. So this is sort of like square and rectangle. If you know something's a square, then you know it's a rectangle. But if you know it's a rectangle, you don't know it's a square. So continuity does not necessarily mean it is differentiable, but differentiability guarantees continuity. And so this is the introduction to differentiability. Thank you.